Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the torsional rigidity and torsional stiffness of a circular shaft. The strength of the shaft may be considered as the maximum torque or power transmitted by a given shaft without exceeding the maximum shear stress. So it depends on the polar modulus of the cross section of the shaft and the maximum shear stress of the material. So torque transmission capacity of a shaft depends on the polar modulus and maximum shear stress. But for a given material, maximum shear stress limitation is same. So for a given material, torque transmission capacity only depends on the polar modulus of the cross section. So torque carrying capacity or torque transmission capacity is only depends on the polar modulus when the materials are same. Polar modulus of a solid shaft is given by 5 by 16 d cube and polar modulus of a hollow shaft is given by 5 by 16 d naught cube into 1 minus k to the power of 4, where k is the diameter ratio di by d naught. Now coming to the torsional rigidity, it is the torque transmitted by a shaft while undergoing unit angular twist in unit length. How much torque a shaft can transmit while undergoing unit angular twist in unit length. So you know the torsion equation. A part of the torsion equation is T is equal to g theta by L into J or Gj into theta by L. How much torque a shaft can transmit while it undergoes unit angular twist per unit length of the shaft, that is the torsional rigidity of the shaft. That is given by torsional rigidity is T by theta by L. So it is equal to Gj. So the torque transmitted while the shaft undergoes unit angular twist in unit length is given by Gj. So it is a material property and a cross-sectional property. So material property is G, modulus of rigidity, and cross-section property means it is a polar moment of inertia. So it depends on the material and polar moment of inertia. Whereas torsional stiffness is the torque transmitted by a shaft per unit angular twist. While the shaft undergoes unit angular twist, how much torque it can transmit. It is a material specific and a shaft specific. Two shafts made up of same material can have different torsional stiffness even though the polar modulus are same. Let us consider two shafts having same cross section but different lengths. Now the shaft which is having more length will undergo more angular twist and that will have less torsional stiffness compared to the other shaft which is short in length. Even though the cross sections are same, materials are same, the one which is longer will have less stiffness compared to the one which is short. So torsional stiffness is a shaft specific. So whereas the torsional rigidity does not depend on the length of the shaft. It is defined as a torque transmitted per unit angular twist per unit length and it is given by Gj. Whereas torsional stiffness is torque transmitted per unit angular twist. So this depends on the shaft length also. So it is given by torsional stiffness is given by Gj by L. So it is a material property, it is a cross-sectional property and also depends on length. Length increases, torsional stiffness will decrease. Whereas other two values they increase, the torsional stiffness will increase. So to increase the torsional stiffness of a shaft, you should always have a material which is having high modulus of rigidity, higher polar moment of inertia and short length. So this will have higher torsional stiffness. So when materials are same and shaft lengths are same, the torsional stiffness depends only on J. When you are comparing two shafts, if the materials are same, so G values are going to be same, and if shaft lengths are same, this also is going to be same. The torsional stiffness depends only on J or polar moment of inertia. When shafts are having the same material, torsional rigidity can be compared by comparing polar moment of inertia. So when the shafts are of same material and length, whether it's a torsional rigidity or torsional stiffness, one which is having higher polar moment of inertia will have a maximum torsional rigidity and maximum torsional stiffness. Let us work out an example. Show that a hollow shaft is stronger and stiffer than a solid shaft for the same weight, length and material of the shaft. So it is given that weights are same, lengths are same and materials are same, and one is a solid shaft, another one is a hollow shaft. You have to prove that hollow shaft is stronger and stiffer than the solid shaft. So the condition given is weight of solid shaft is equal to weight of hollow shaft, and lengths are same. Length of solid shaft is equal to length of hollow shaft, and materials are same. While materials are same, you will have the same rigidity modulus and same specific weight, that is weight per unit volume will be same. So weight per unit volume is a specific weight. I have denoted it by gamma. So specific weight of solid shaft is equal to specific weight of hollow shaft. Now weight of a shaft is given by volume into specific weight, because specific weight is weight per unit volume. So weight of a shaft is volume into specific weight. So here volume of a shaft is cross-sectional area into length. So volume is given by cross-sectional area into length. So that multiplied by specific weight will give the weight of the shaft. So for solid shaft, the weight is pi by 4 d square, which is the cross-sectional area into length. That will give the volume multiplied by specific weight. So that is the weight of the solid shaft, and you can equate, because weights are equal, so you can equate to that of a hollow shaft, pi by 4 into d naught square minus di square into length into specific weight. So I just equated the weights. Now the gamma s is equal to gamma h, because materials are same, specific weights are same, lengths are same, so that will cancel out. Pi by 4 will cancel out. You get d square is equal to d naught square minus di square. So from the given conditions, you are getting d square is equal to d naught square minus di square. So you have that condition, d square is equal to d naught square minus di square, okay, or d square is equal to d naught square into 1 minus k square. Okay. So I have taken d naught square outside, so you will get 1 here, and you will get di square by d naught square, or di by d naught square. Di by d naught is k, so k square. So d square is equal to d naught square into 1 minus k square. So we have this relation from the given data. Now we have to prove that hollow shaft is stronger than a solid shaft. And to prove that, we have to prove that polar modulus of hollow shaft is greater than the solid shaft. So when materials are same, to show the shaft is stronger than the other, you have to only compare the polar modulus. So you have to take the ratio ZP, polar modulus of hollow shaft, to the polar modulus of solid shaft, and the ratio should be greater than 1. So if it's greater than 1, then hollow shaft is stronger than solid shaft. So comparing that polar modulus, taking that ratio, we get pi by 16 d naught cube into 1 minus k to the power of 4. This is the set P of a hollow shaft divided by set P of a solid shaft, pi by 16 d cube. Now pi by 16 cancels, you get d naught cube into 1 minus k to the power of 4 divided by d cube. So this is the ratio of set P of hollow shaft to set P of solid shaft. So I am going to substitute for d in terms of d naught. Okay, we have already got a relationship d square as d naught square into 1 minus k square. Okay, so I can substitute for d. D is d naught into 1 minus k square raised to half. So d is d naught into 1 minus k square raised to half, or d cube. So d I am substituting d naught into 1 minus k square raised to half. This is substitution for d cube. So you will get on numerator you have d naught cube into 1 minus k to the power of 4. Denominator you have d naught cube, okay, into 1 minus k square is to half raised to 3. So that will make it 3 by 2. So 1 minus k square raised to 3 by 2. Now d naught cube cancels. 1 minus k to the power of 4. I can split this into 1 minus k square into 1 plus k square. Okay, so this is in the form of a square minus b square. So you can write it as a minus b into a plus b. The same way I have written this as 1 minus k square into 1 plus k square. In the denominator you have 1 minus k square raised to 3 by 2. 3 by 2 is 1.5. So you can write it as 1 minus k square into 1 minus k square raised to half. So 1 plus 1 by 2 is 3 by 2. Okay. So I split the denominator term also into two terms. So now 1 minus k square cancels. You have 1 plus k square divided by 1 minus k square raised to half. In this expression, we know k is a diameter ratio and k values can be between 0 and 1. It cannot exceed 1 because it's a diameter ratio di by d naught. So di by d naught should be always less than 1. Okay, and it should be greater than 0. Di by d naught 0 means it's a solid shaft. Di by d naught 1 means the shaft does not exist. Di and d naught both are equal, so that means thickness will become 0 and the shaft will not exist. So the value of k should be between 0 and 1. So any value between 0 and 1, this numerator will be greater than 1 and denominator will be less than 1. Denominator will be less than 1 because you are subtracting a positive quantity from 1 and taking the root of that. So this should be less than 1. So numerator is greater than 1, denominator is less than 1. Now the ratio is always greater than 1 for any value of diameter ratio k. So we have proved that a hollow shaft is stronger than a solid shaft for the same weight, length and material. Now we have to prove that it is stiffer or more rigid than, in this case, since the lengths are same, we can even prove that it's more rigid or stiff. Now to show that a hollow shaft is stiffer than a solid shaft with the same material, we have to prove that polar moment of inertia of a hollow shaft is greater than that of a solid shaft. Because materials are same, when materials are same, to compare the stiffness of the shafts, we have to only compare the polar moment of inertia. So if you take the ratio of polar moment of inertia of hollow shaft to solid shaft, that ratio should be greater than 1. If it is greater than 1, then hollow shaft is stiffer than solid shaft. You can also say that it is hollow shaft is more rigid than solid shaft. Now here J of hollow shaft is pi by 32 into d naught to the power of 4 into 1 minus k to the power of 4, because it's a pi by 32 into d naught to the power of 4 minus d8 to the power of 4. Once you take d naught to the power of 4 outside, you can write in this form. So that is a polar moment of inertia of a hollow shaft. Now for a solid shaft you can write it as pi by 32 d to the power of 4. Now pi by 32 cancels, you'll get this expression. Initially we got an expression from the given condition as d square is equal to d naught square into 1 minus k square. So d square you can substitute as d naught square into 1 minus k square. Now d to the power of 4 is there, so d square we have substituted this, so d to the power of 4 is square of that. So you get d naught to the power of 4, so that will cancel out. You will have numerator will have 1 minus k to the power of 4, denominator will have 1 minus k square whole square. So now d naught to the power of 4 will cancel, you get 1 minus k to the power of 4 divided by 1 minus k square whole square. So numerator 1 minus k to the power of 4 we can split into 1 minus k square into 1 plus k square. Here this I write it as a product of the 1 minus k square, product of 1 minus k square. So 1 minus k square into 1 minus k square. So 1 minus k square will cancel, 1 plus k square by 1 minus k square. Here again you can show that the ratio is greater than 1 because k is a positive quantity lying between 0 and 1, and the numerator is going to be always greater than 1 and denominator is always less than 1, because any positive value lying between 0 and 1, this k square is going to be less than 1 and 1 minus that quantity will be less than 1. So this quantity is greater than 1 and denominator is less than 1, so the ratio is always greater than 1. So this proves that hollow shaft is stiffer than a solid shaft. Now, hence we have proved that hollow shaft is stronger and stiffer than a solid shaft. So it also proves that torsional rigidity of the hollow shaft is greater than that of a solid shaft. That's all for today. Thank you for watching.